Hello. So this is the part 2 of the introduction lecture where we're going to do some coding on this Curiosity Nano board using the button and the LED located there. So the first you have to do is to look at some data sheets, I think. So we have two data sheets, one for the Curiosity Nano, and this is actually called the hardware user guide. And we have the bigger one that's more important. That is the data sheet for the AVR DB family, including the 48 pin variant. So first of all, can look shortly at this. I already told you have these debugger circuits in the end here, and then here is the microcontroller we are dealing with. There's some crystals and stuff here, and here's the LED, and here's the button. But sometimes it can be difficult to figure where it's actually connected. So instead of reading all the datasheet, like scrolling through everything, it's very smart to use this side menu. So if you go to the hardware user guide, there you can find some connectors and peripherals under one of these tabs. And if you find the connections, you can look at all these pins and where they're connected and what they're connected to on the AVR chip. And if you look closely, you can see you have SW0 and LED 0, so switch 0 and LED 0 here, and they're also marked here. And these are connected to PB2 and 3. So we will be using PB2 and 3, which means port B, pin 2 and pin 3. So then we can look at the bigger data sheet. And in this data sheet, you can find some of the similar things. You can look at the pinout for the different package types of the chip. Like this is the package type we're using. But it won't give you a lot of information for this course. This is more relevant if you're going to make your own microcontroller circuits. Anyways, so you can also look at this I/O multiplexing and considerations, and you will see under this tab here. Can try zooming. You can see this is the variant we have, and it doesn't have all the same stuff as the 64 pin variant, so that's something you have to be aware of. Sometimes the data sheet mentions some peripherals that doesn't actually exist, like these port pins, port E 4 to 7 doesn't exist on the 48 pin variant. So, but we are more interested in the port functionality now, and we can find the port functionality in chapter 18. And you can see here you can read about the features, and these parts of the data sheet they're completely the same. So for every chapter, you have some features overview where it sometimes shows a block diagram that I also showed in the lecture with all these different that I'm going to show in the lecture. So here you have in the next lecture. Here you have the pin, and you have some logical circuits and some stuff. And you can also find the functional description that tells you how to initialize some peripheral and operation. But normally when you have already read this and figured out how things work, you will just go to the register summary straight away. And then you have all these registers that are relevant for this peripheral. Sometimes you also have to involve another peripheral to make things working, but yeah, we'll come back to that later this semester. So today we're going to use a couple of different registers, the direction register, out register, and in register, and maybe some of the others later on. But mainly these. So the direction means, and that we can figure out if we press on it, we can find this is a data direction. So if it's if one bit, let's say the first or the 0th bit is a 0, that means the 0th bit is also an input. So you can read the input voltage in the in register. If it's a 1 or a high voltage, then it's considered an output, and then you can use the out register to decide if it's going to be 1 or 0 or high or low. And some other facts about these figures. You can see there's a access for all these bits. Sometimes you only have read access. Here you have both. You also have a reset. So reset is 0. That means when you're starting this microcontroller, it will automatically be configured as input by default. So this will have some interesting implication for us. Yes. So if you go back to the register summary, we have been looking at the DIR. You have some other registers here that kind of does things for us in a effective way, but we'll talk more about those later. We have the out register. Note that this is also 0 from reset value. And here it describes what it actually does. So let's now go to the Microchip Studio and make a project. So we'll try. It's not easy to magnify this image, but I go to press File and I choose New and Project. And then I will choose some funny name. And I will choose GCC executable project. And then I will get some choices. I have to describe what microcontroller I'm using. And I can choose it from the list. And then I'll generate the project where I can put my main file and the other files. So you can see in this corner, I have the solution with some file structure where I can actually add new items. That's something we'll do later on. And I have a main file here. And this is under the tab Solution Explorer. This is very useful. And here I have the already made start of the project. And it includes the AVR IO library, which contains lots of interesting and useful stuff. It defines an main function that doesn't take any arguments. And in here, there's a while loop that will continue forever. So if you're going to do anything, we might want to put it in this main function. And we can also have some global definitions and declarations outside of the main function. So what we want to do first is try to make some LED blink. And we know it's located at PB3, port B3. So what we can do is use the struct formulation, port B direction, and then we can use equality. Yeah, and by the way, if you look at the small camera, I haven't connected this yet. So if I connect it now, it should pop up because Microchip Studio should recognize it. Yes, so there it popped up, and it recognizes the debugger. And speaking of the debugger, you can also find it here. If you go to Tools and Device Programming, you can choose the debugger tool. Don't choose the simulation. If the simulation is the only one that's recognized, you might have some problems with your connection. It could be just a software problem with the Microchip Studio, but it could also be that your USB cable is not actually having any data traces, so it's only for power, which is quite stupid in my opinion. But anyways, that's how things work this day. Lots of equipment are bought with USB power. So yeah, if you find if all these things are correct, like the interface, that's just the debugger interface. I guess you won't be using JTAG or something else, but yeah, and this is the right microcontroller. Then you can press apply, and then you can also read the signature and the target voltage of the chip. So here you can see the signature, and 3.3 is the target voltage. So you have also some opportunities here to change certain things, like you can change the tool setting, you can change the voltage. Don't do that. That's a bad idea for the components on the board. Yeah, so I don't think it's anything more interesting here at this time. But yeah, if you're programming a chip with an external debugger, you have to go through this menu normally. Okay, back to the code. So port B dot direction, and that's equal to the PB3. So I can do like this, make a bit mask. So I shift this bit mask that is just like it starts out with just zeros, like this, and then I make this I shift one 3 spaces, so it becomes 1, 2, 3, 0, 1, 2, 3, right? And yes, I can do it like that, and I will show some other ways of doing it. So as you can probably see, this number on binary, that's some exponent of 2. So you could also write, let's say, 8 in decimal. That will be the same. Or you can also make it in hexadecimal. So in our while loop, we can do something with the output, port B dot out, and then if we're going to blink it, you can there are several things we can do. We can use the set and clear registers that I can show here. So if you go back here to summary, you see we have like out set and out clear and out toggle. So maybe we'll actually use out toggle. So this will change the state based on its last state. And then we can use the same variant, but now I'm going to show you a slightly different way of doing it. So there are some definitions in AVR.io.h. So we will try to use one of those. So if you can see there's like specific pin definitions. You have this one, and you also have, I can copy this line. So this is called BM, but you also have a BP, and like this. So if you're going to use the bit position, then you will have to do similarly like this. If you're going to use the bit mask, it's defined as the same thing as this one. And if you want to figure out what these things actually mean, you can go to implementation by right-clicking, and you can find all these definitions. And as you can see, there are lots of definitions. So most of these bit positions and bit masks that you will use in this course are already defined here, and it will make the code more readable. Not necessarily more portable, but more readable at least. Yes. So we can comment out this one. If we want to run this code, you can of course enter debugging mode, but I would rather say it's easier to just go for start without debugging. And then it compiles and flashes the code. And now we can see this LED is not visibly blinking, but it is blinking. It's just blinking very, very quickly. So I want to show you also what happens if I don't have anything in port B. So you said it is maybe so it was flashing, and then it started shining again, and that's because I can draw it quickly. So on this circuit board, if this is the pin, that can be high or low. The circuit is actually like this, where you have the high voltage here. So you have to drop this down to 0 voltage, and then the current will go here, and the LED will shine or be on. So yeah, this makes the logic slightly backwards, but you don't have to be worried about that. It's just so why does it start when I just put some things in the port B dir or direction? Well, if we go back to the register description of out, register summary, and then look at out, we see all these are 0. And as when we are activating it as a output with the direction, this will be like it will happen straight away. This value will be given to the out driver. So if we want to continue blinking, but we want to do it like so you can actually see it, you have to have some more libraries or at least some functionality. And we will like to use a library called delay, or a file called delay, which is located in utilities or util. And if you're going to, so delay, it has a function called delay ms or us, depending on if you want to use microseconds or milliseconds. So now this will be 1 second, and this is calculated by from the CPU speed, or the CPU frequency. So we have to give the frequency, unless it will just define something on its own. That can be wrong. So then we have to give, that must happen before this one is included. Define, and then it's F CPU, and it's the default value on this chip is actually 4 megahertz, and this is unsigned long, so we have to put this ending. You don't always have to put the ending if it's a uint and stuff like that. 8-bit number, it's fine, but this has to be specified as a unsigned long. So if you try this code now, then I can try end sharing. So now we can see it's blinking. Okay. So now we want to do something else. We want to use the input also. So what I can do, I can just make an if test. So I want, when the button is pressed, I want it to be lit. So we can have if, and then I have to, so this is already, the button is already connected to the same register or the same port. So we can use, since there is by default zeros, this is an input. So if I just check what the state is, and I can check for the specific mask, and this was located on 2, but I can do it like this, so it's a bit nicer. So if this is if this specific pin and this is a bitwise and, so that means if I can describe that here. So port B dot in, let's say that's okay, it's like this, I guess. And you have this bit mask. And that's this number. So now we see the bitwise calculation here with an and will just become okay, maybe and okay. So we have zeros all the way. But if this one becomes a 1, then this one becomes a 1, and everything that's not zeros here will be considered true here. Even if it was like if it for some reason would be like this, and this one is false, then this one will be still true. So yes. So I will erase this for avoiding confusion. And if this is true, then we can turn on the LED. And remember the LED was, so now I can use outset. it's the LED is inverted, so we have to actually use out clear. And then it's pin 3 bit mask. And then we don't have any other conditions, so we can just have it on unless this is true. Outset equals pin 3. So if you don't want it to switch, I guess you have to have a else like this. So the first line will be considered a part of this else. So actually here we can also do like this. That's fine. So I already know this is not going to work, but I can try it anyways. So now it's off. And if I press the button, yeah, so now it's blinking kind of. And this is because we haven't defined very specific things here. So if I go back to Paint, this is the pin, and here's the button. And it's connected to ground. So it's not like it's giving a high voltage when you're pressing it down. It's just giving a low voltage. But what happens when the switch is not connected to anything? Well, then you don't have a defined voltage on this pin, and that's why it was just kind of flashing without any good explanation in this code I run now. So the solution to this is to have a pull-up. And if you look at the circuit or the datasheet, not here, but here, and we go to the overview, we can see there's actually a pull-up enable here. Here's the pin, here's the resistor, here's the transistor, and you have a pull-up enable that's also, it also needs the direction to be an input. This is a negation or inversion. So if we use pull-up enable, then we can define this voltage. And where can we find these settings? Well, we have to go back to the register summary, and then we can look here. And we have some pin config, we have pin 0 control, all the way to pin 7 control. And here you can say there's like some in level, pull-up enable, and some other stuff. And we will look at the pull-up enable, and also for simplicity, we'll look at inv-n. So if we go to pin 0, or we can actually go to this, this is all the pins. So pin n control, they're the same. So inv-n, it inverts the I/O in input and output. So this makes our settings slightly more logical for us. And here we have the pull-up enable. So let's do that for the pins we have here. So first of all, port B dot pin 3 control. And then we will use this one. This is a logical or a bitwise OR and equals. So this will do the same as this set. So it will set bits, but it won't erase bits. So this is kind of slightly more secure if you don't want to change any of the other settings. So this is very normal to use instead of equal when it comes to settings for configurations and stuff in registers. And then we have port and pull up enable, but we're not going to use that one first. We are going to use the inv-n because this is the LED, right? We don't want to have a pull up on the LED. That doesn't make any sense. So here we have that one. And we can do the same for the other pin. So by the way, learning all these definitions, that's kind of something that takes a bit experience and takes time learning. But you can do the same, go to implementation, and then you will find a whole list of all these things. So yeah. And it will slowly come to place in your mind. So I do the same here. Port in and I will also make another bit mask here, or like I will combine these two bit masks for the pull up enable. And now this makes more sense also, because this wasn't making sense if it's logically 0. Or when you have a pull up, it doesn't make sense to do this. Then you have to do this if the button is connected to ground. Anyways, now we can also change this. Oh, set and out clear. Yes, no, you don't have to. This one has to go. Compiling, flashing, and then I will turn off the sharing. Oh, right, stop share. Stop share. And when I press the button, you can see it lights up. So this is a very simple program. And it doesn't give the complete solution of the first lab, but it gives some indications. So I think that's enough for this demonstration. Thanks.